So just to remember that the empirical formula was C3 Cl2 F6, and we'll repeat that X times, and that will give us the molecular formula. Well, when we add all of these together, it comes to 220, assuming that, of course, you've got 3 carbons, which equals 36, assuming that the chlorine isotopes are chlorine 35 times by 2 is 71, and fluorine times 6. Add all of that together, and that gives us an empirical mass of 220. So empirical mass times by the number of times it repeats itself is equal to the relative formula mass. And therefore, we were told that the relative formula mass is 220, and therefore 220 times X equals 220, and therefore the empirical formula in this case equals the molecular formula. So there's 3 possible scenarios for our structures. One of them could contain the 2 chlorine 35 isotopes. And 6 fluorines. One of them could contain the chlorine 37 and the chlorine 35. Fluorine. And one of them could contain both of the rarest isotope of chlorine, which is chlorine 37. Don't forget to draw the whole structure. Now don't forget that the molecular ion peaks are caused not by the molecule, but by the fact they've had an electron knocked off. So don't forget the positive charge. Now for the next bit is to look at the ratio of the peaks of these ions, and that was the tricky bit that a lot of you struggled with. So let's explain this word working out. If we remind ourselves and go back to the start of the question, we know that the 2 isotopes, chlorine 35 and chlorine 37, have respective abundances in the ratio of 3 to 1. So the total abundance is 4, and therefore the number of chlorine molecules, or the proportion of chlorine molecules having a mass of chlorine atoms having a mass of 35 is 3/4. So every 3 out of 4 of them will be at chlorine 35. Now the rarer isotope, chlorine 37, every 1 in every 4 of the chlorine atoms will be chlorine 37. So let's work out the abundance of this molecular ion here. We've got 2 chlorine atoms, each with an abundance of 3/4, and that is why we multiply the 2 together, because there are 2 chlorine atoms per molecule. Let's look at the molecule again. Each with a mass, 1, 2, 3, each with a mass of 35, and that is why we multiply the abundance twice. So that's 3/4 times 3/4, which is 9/16. The second molecule, this one here, we have 2 chlorine atoms, which is where you get the 2 from, one of which has an abundance 1 in every 4, that's the chlorine 37, and 3 in every 4 is chlorine 35, and that comes out at 6/16. So the ratio is 6 to 16 of this molecule here, this molecular line here. So finally, to get the proportion of molecules which contain the rarest isotope, chlorine 37, well, there were 2 of those chlorine atoms in the molecules, that's 1/4 times 1/4, which comes out as 1/16. So again, if you divide through by the smallest, the ratio comes out to 9/16, to 6/16, to 1/16. Divide 3 by 16, so the ratio is 9 to 6 to 1. You divide through by 16. It's not been asked for, but if you were asked to sketch the peaks and the MZ, don't forget that on a mass spectrum, there's the mass to charge ratio, there's the abundance, so the ratio is 9 to 6 to 1, where this is C3, Cl2, both isotopes 35, F+. So that's that isotope there. So the mass to charge ratio is 220. The mass charge ratio of this isotope, and this is the mass to charge ratio of this isotope. Question 3 was asking you, again, this is simple AS isomerism. So you've got an alkane with a molecular formula C5H12. And the best way of doing this, solving this problem, is to construct skeletal formula for C5H12. So you've got the straight chain isomer. So it's got 1, 2, 3, 4, 5. And then you must have the branched isomers. So if we now take a carbon from the end here, take this one off, one, two, three, and you can branch it there. Is there anything else you could do? Well, yes, you could take off this carbon here and branch it yet again. You can't do any more branching, and therefore the number of isomers must be 3, and these are chain isomers. That was some easy peasy AS chemistry. Now let's move on to the next part of the question. The next part of the question asks you to look at the 3-dimensional representation of 2 enantiomers. So immediately we know we're looking at optical isomerism, and they need us to draw the structure. The way I would tackle this is I would draw, first of all, the 2D structure of 2-hydroxypropane nitrile. So that's expecting you to know that a nitrile group is CN. Prop, so it's 3 carbons, 1, 2, 3, and it's got a hydroxy group on carbon 2. By drawing the 2-dimensional structure, you can see at a glance that the asymmetric carbon, the chiral centre, is carbon number 2. So now we go about drawing the 2 enantiomers. Do not forget your mirror plane. Draw 1 enantiomer by starting with a tetrahedral structure. So 2 groups in the same plane, 1 bond coming out at you, so we show a wedge, and the bond behind it we can't see, so we draw as a dotted line. Please practice drawing these. It's like an umbrella that's blown itself inside out. Get some weird and wonderful student drawing of these. So to draw its mirror image, you've got two bonds in the same plane, the wedgie bond opposite, and the bond behind it you can't see. Select any group. So there's a hydrogen, so it must be reflected in the mirror there, get rid of that. There's the nitrile group, I'll stick that there, it doesn't matter where it goes. There's its mirror image. There's the hydroxy group, I'll put it there, and therefore that is reflected there. Make sure the oxygen is bonded to the carbon, not the hydrogen bonded to the carbon. And then we have finally a methyl group. There are your two enantiomers. Be careful when you answer the next question how they can be distinguished. You must mention the term plain polarised light. So by pass plain polarised light through a solution of the enantiomers or separate enantiomers the solutions will rotate light in opposite directions. Take care to write in full sentences, but you make sure you use the term plain polarised light. Plain polarised light. Remember the rule? Read the full question. Butan-2-ol reacting with conch sulfuric acid to make 3 isomeric alkenes. First thing you had to do, name and outline a mechanism to show how any one, you don't need to do lots of mechanisms, of the alkenes is formed. 2, explain how this reaction can lead to the formation of 3 alkenes. And then the name of the mechanism. Well, because it's a mechanistic approach, I'm not even going to attempt to name the mechanism until I've outlined the mechanism. Now, to outline the mechanism, it means curly arrows. It says describe the mechanism, use curly arrows. So it's reacting with concentrated sulfuric acid, and we're ending up with an alkene. So let's draw butan-2-ol first of all. So when we studied alcohols, and I can't help but do it, is put the lone pair on the OH. And if you remember your sulfuric acid structure from when you did alkenes, if you remember the Starship Enterprise, where it's the back of the ship is your OHs, and the starboard is this bit here. There's your Starship Enterprise. So you can remember your molecule of sulfuric acid. So we know sulfuric acid is a strong acid and it readily loses protons. So the first step in the mechanism is that this proton here is readily lost, and therefore this bond is going to break, and the oxygen being more electronegative will take that away. We've got a lone pair on the oxygen here which will accept that proton. The first step is protonation. So if this section becomes protonated, we then end up with an alcohol with a weird charge. It has behaved as a Bronsted-Lowry acid. It has accepted a proton, and don't forget your positive charge. And therefore the Starship Enterprise here has lost a proton, so what's left behind is O minus, where one of its engines has dropped off, S, O, 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 H. Now we want to end up with an alkene, and that's a double bond. And if we now look at the protons that are adjacent to this protonated OH group, all of these can be lost. So they can't just drop off themselves. A base has to come along. Well, where is the base? Here's the base, our hydrogen sulfate ion. So we could take any one of these protons off. So it just happens to be closest to that one, so it can move that one. Now, if this is accepting a proton, remember that this hydrogen can't have more than one bond, and therefore it can push its electrons between these two carbons here. This carbon now would end up with a total of 1, 2, 3, 4, 5, can't do it, and therefore the water drops off. Look at your curly arrows again, all flowing in the same direction. So in this case, the sulfuric acid is regenerated, so it acts as a catalyst. So your H2SO4 comes back again. Water has been knocked off, don't forget your H2O. And in this case we formed butene. Now I'm going to draw the crab form notation. So there's a hydrogen, CH3, CH3, H. So I have formed butene. And in this case, the priority groups using the Carn-Ingold rules are these, because carbon has got more protons than hydrogen, so these are the priority groups. Priority groups are both on the same side, Z, zusammen, same side, and therefore we know that we formed Z-butene. So there's Z brackets butene. Now it could have been that a proton from the other side could have been taken. So how do we end up with two geometric isomers? So two geometric isomers of butene could be formed, could arise due to, and remember this for geometric isomers, restriction of rotation about a bond, the double bond. So that explains the second isomer. So let's draw the structure of it. So you could have E entgegen E-butene. So how do you explain the formation of a third isomer? Well, if we look at the structure, a proton could have been taken instead of carbon 3, could have been taken off carbon 1. So one of these could have been removed. So let's tell the examiner that. But1ene, a position isomer, would be formed if a proton or a hydrogen was lost from carbon 1. One thing I nearly did was to go back and name the mechanism. So now instead of trying to guess which mechanism it is, you look and you can see that a molecule has been eliminated, but a molecule of water has been lost. So the mechanism, because a small molecule has come out, is elimination. Or you could say it's acid catalyzed elimination. Elimination. So in this question, we're looking at a synthetic group. And the first question is asking us how to name compound F. Well, first of all, if we look at these groups here, we know they're carboxylic acids and we know they end in oic acid. Also, we can see there are 2 carbons sticking off the chain here, and if we number the carbon atoms, let's call that carbon 1, 2, 3, 4, we have a methyl group on carbon 2 and a methyl group on carbon 3. The name of the longest chain therefore is 1, 2, 3, 4. It's a bute. So the methyl groups are on position 2 and 4. So sorry, on position 2 and 3. So it's 2, 3, dimethyl, butane, dioic acid. Some of you may have squeezed in 2, 3 dioic acid, but since the carboxylic acid groups are on the end, you don't really need to name their positions. Don't forget the E, butane or butane dioic acid. Di, because there are 2 oic acids, dimethyl. So let's write that again. 2, 3, di, because there are 2 of them. Methyl, because there are 2 methyl groups. Butane dioic acid. Go on to the next page. Step 1, let's go. So step 1, reagent. Now it's common when you write out reagents to give the name. Hydrogen bromide. Why would you give the name? Well, if it's more complex formula, you get it wrong if you got the wrong formula. And on reagent bottles, you tend to have the name. We're converting an alkene to a halogenoalkane, and therefore it was electrophilic. An alkene will undergo addition reaction. In the second step, the reagent that we're using, do not just write Cn minus. So either potassium, cyanide, and hydrogens, because that converts it to hydrogen cyanide. And the mechanism, so the mechanism, we've got halogenoalkane, and we're substituting the bromine group with the cyanide, so it must be nucleophilic substitution. Helpful if you can get the correct spelling, it's 1L. Now step 3 on your toolkit is converting a nitrile to a carboxylic acid. This group here, the nitrile group, is really unstable or labile. And it's easily broken down or hydrolyzed. So that reaction there is hydrolysis, breaking down using water. And just to help it along, we use some aqueous as the water acid, and that's a hydrolysis reaction to give a carboxylic acid. When you were looking and revising for your AS paper as well, you had to know simple tests for organic molecules. And straight away, you can see that this one here is a carboxylic acid and this one here is an alcohol. And therefore, there's a variety of reagents that you should be aware of to distinguish between these 2 molecules. So what would you observe? What is the reagent? What would you observe when it's added to each compound and the test tube is shaken? Well, first of all, because we know this is a carboxylic acid, you should even know from year 9 that carboxylic acids, or all acids, fizz. So think about throwing a body into a vat of acid and it dissolves and it fizzes. So something that dissolves and fizzes. So the most common reagent for any acid is something like a sodium carbonate, And because F is a carboxylic acid and G is an alcohol, alcohols are not strong acids at all. In fact, it's really hard to lose a proton, whereas this proton in carboxylic acid comes off. So if you add sodium carbonate with a carboxylic acid, you would see effervescence or fizzing. Don't write down carbon dioxide will come off because you can't see that. So you shake it and it would effervesce. And G would give no visible change. Or you may have been thinking back to your alcohols and you remember that if you warm alcohols, certainly primary and secondary alcohols, and this is a primary alcohol because it's attached to a carbon with two other hydrogens, you know that primary alcohols react with acidified potassium dichromate. Which is orange. And therefore with F, acids can't be oxidised any further, so you would get no visible change. But with your alcohol, it's an alcohol, traffic lights, orange to green, you're going to jail. So orange solution becomes a green solution. As the dichromate, the chromium is reduced from +6 to +3, so it goes from orange to, so the dichromate, which is orange, gets reduced to Cr3+, and the alcohol gets oxidised. So either one would have done. You also know that if you put a metal in any acid, it will fizz. So there's the acid. So you could have added magnesium metal, is a good one. Not sodium because it will blow up. Not copper because it's not reactive enough. Magnesium's reactive enough. And with the acid, therefore, it would also effervesce or fizz. And with the alcohol, because it's not acidic enough, you would get no visible change. So either one of these chemical tests would have done, but it's wise to learn them, especially carboxylic acid, because everyone forgets that. The next question asks us to draw the repeating unit of the polymer. So let's just remind ourselves of the structure of F. And the G, which is obviously a diol. So we've got an alcohol and we've got carboxylic acid, and again on your toolkits you know that alcohols and carboxylic acids react together to form esters, and therefore they react to form esters with a loss of a small molecule, and the loss of the small molecule is water, so we would lose a molecule of H2O. So there's a molecule of OH to get our ester. So the repeating unit in this case, carbon skeleton has not changed at all. So it's C, double bond O, and the alcohol is O. And there's our ester link. And then I'll put a hydrogen there, bear with me. So now that then goes off to bind with another polymer chain. And this goes off to bind with another alcohol. So I'm going to put brackets around it to show that's the repeating chain.